Hello everyone, and welcome back to another episode of Central Physics Reviews, where today we're going to be reviewing units, dimensions, and dimensional analysis. So right off the bat, let's talk about this idea of a dimension. So in this context, dimensions have nothing to do with how we normally talk about living in a three-dimensional world, or a piece of paper being a two-dimensional object, or anything like that. In this context, a dimension is just a kind of thing that's being measured, or a type of measurement that's being performed. So for our purposes, let's just say that the working definition of a dimension is really just a type of thing, right? So when we talked about what physics is in the last episode, fundamentally physics, we said, was about describing things that happen in the world. And the point of dimensions, basically, is to classify or categorize the kinds of things that we can describe. So to be a little bit more concrete or specific about what these dimensions can be, let's list out a couple of them. So first of all, we can definitely measure time, right? How much time passed between one event and another. Separately, we can measure distances or lengths, which is just a measure of how much space is between one object and another. Or if you're talking about lengths, that's also a distance, because that's just how much distance is between one endpoint of the object and the other endpoint of the object you're measuring. So that's also just a length. And so if we look at these things, we can kind of see why they go into different categories, right? Because for one, you can't really compare different times and lengths to each other, right? If I asked you, is 10 inches less than, greater than, or equal to 5 seconds? You probably would look at me kind of weird, because that's a completely nonsensical question to ask. And by the same token, we can't add or subtract different times and lengths, right? 10 seconds or 10 inches minus 5 seconds, or 10 inches plus 5 seconds, is again a nonsensical mathematical statement. But something that we can assign a little bit of sense to is multiplying or dividing different dimensions. And at first it seems kind of strange, right? If I say 10 inches again, divided by 5 seconds actually means something, you might scratch your head for a little bit, but we can interpret that quotient, right here, let me write it down, 10 inches divided by 5 seconds. We can interpret this quotient as just a ratio between two different things we've measured. We've measured something to be 10 inches, some length, and we've measured some time to be 5 seconds. And this quotient that we've computed here, right, we can calculate it. This is just 2, which has dimensions of length divided by time, or units of inches per second. This new quantity is actually interpreted as a speed, right? Because the ratio of how much something moves along to how much time it takes to do that thing is just the speed of that thing itself. So this is an entirely new dimension that we got by dividing length by time. We got the dimension of speed, or velocity if you like. We're also free to multiply these things together, right? Multiplying time and length together doesn't give us anything intuitive, certainly doesn't give us anything we're familiar with, right? We don't know of anything that's measured in inches times seconds. But I can give you a different example. Commonly in the workforce, if you have a project where you have, let's say, 10 people working on a project, and each person puts in 5 hours of work, so you can multiply 10 people by 5 hours, and you get out 50 people hours. And this product, people hours, is a measure of the total number of time that's been put into this project by all the people. And so the actual dimensions are the dimensions of people multiplying the dimensions of hours. But let's do something a little bit more physics-oriented, right? Let's multiply length by itself. If we take this 10-inch measurement that we made before, and we make another 10-inch measurement and multiply it together, so we get 10 inches times 10 inches, we get 100 inches times inches, or inches squared. And so this quantity is another thing that we're familiar with in physics or geometry. It's just an area, right? Areas are measured in square inches. And so that's a new dimension again. By the same token, if you multiply in another length, you'll get something in inches cubed, or a volume, which is another dimension as well. So what you see is that even though these different dimensions are completely separate from each other, you can't compare them, you can't add them or subtract them, some of them are related to one another. So for example, length, area, and volume are all clearly related to one another. And this kind of distinction leads to the convention of fundamental quantities or fundamental dimensions versus derived quantities or derived dimensions. And so conventionally what we say in physics is that time and length are fundamental quantities. And everything else, at least on this list, speed, area, and volume, can be derived from those quantities just by multiplying them together or dividing one by the other to take their ratio. Now, the reason that I say it's a convention is because in principle we could have chosen two different quantities to be the fundamental ones, right? We could have chosen, for example, time and speed to be fundamental, and length would be a dimension that just comes from multiplying speed times time. In principle, we could have done that, but that's not how it's conventionally done, so we'll stick to what the conventions are. Now, certainly these aren't all of the dimensions that we have in the physical world. We can look at a bit of a more comprehensive list here. This still isn't the full list. You can go on Google or Wikipedia to find some more dimensions in the physical world, but these are some of the most common ones. So some fundamental quantities that we have here, we already talked about time and length, but we also have mass. We have electric current, which is, again, a thing of its own, and temperature, which is totally separate from anything else in this list, right? So all of these quantities can't be compared to one another. They are totally separate categories of things we can measure in physics. And on the right column, we have derived quantities, and these are all things that can be specified, their dimension can be specified by multiplying or dividing the dimensions of the fundamental quantities on the left. So if we go through this list really quickly, we've already done speed, right? Speed is simply a ratio between length or distance and time. Acceleration is the ratio between speed and time. It's how much a speed changes over time. So you find that by taking speed and dividing by time. Area and volume we've already done, right? Area is length squared, and volume is length cubed. Electric charge is kind of funny. In this convention, we're using electric current as our fundamental quantity. And so what we have to do is multiply electric current by the time that the electric current is flowing to get how much charge is actually transferred. So this is going to be electric current, I, multiplied by time, t. I don't have the space to write everything out, but there you go. And just a few more left here. So mass density is, by definition, the ratio of how much mass an object has to how much volume it takes up. And notice that, of course, volume isn't a fundamental quantity, but volume is just length cubed. So you can still express all of these derived quantities just in terms of the fundamental ones, right? We can keep going, right? So force is something that you'll find a lot of in physics. You can recall Newton's second law, that force is just a mass multiplied by an acceleration. And along the same lines, we have a concept in physics called energy, and the dimension of energy is just the dimension of force times the dimension of distance, or length. They're the same thing. Or at least they have the same dimension, I should say. And finally, power has the dimension of energy divided by the dimension of time. So power measures the ratio of how much energy is transferred from one system to another to how much time it takes for that transfer to occur. So you can already see that it's at least kind of cool to be able to classify all of these different quantities in this way, but is it actually useful? And the answer is absolutely. The first application of all of these dimensions that you'll probably come across is something called dimensional analysis. And at its core, dimensional analysis is a technique that can tell you if an equation or relationship you see is complete nonsense or at least plausible. So I have two examples to go through here which can kind of demonstrate the power of this technique. In the first example, we just have a simple circle with radius r, and we're faced with just a geometric problem of finding the area of this circle. And let's say in our heads, we're kind of familiar with some quantities related to circles, right? We know that maybe 2 pi r is related to circles, or pi r squared is also related to circles. And if we dig a little deeper, maybe 4/3 pi r cubed comes to mind. And we can't quite remember which one of these is the area of the circle, but we have 3 potential candidates, right? Either the area is 2 pi r, or pi r squared, or 4/3 pi r cubed. Now, if we do some dimensional analysis on this, what that means is instead of thinking of this as a math problem, we think of it as a physics problem where we're measuring physical quantities. We can recognize that area has dimensions of length squared, or length times length. Whereas the radius is obviously just a length, right? So it has dimensions of length. So in this first equation, 2 pi r has dimensions of length. R squared has dimensions of length, so pi r squared does too. Sorry, length squared I mean, of course. And r has dimensions of length, so r cubed has dimensions of length cubed. And the fact that we're multiplying it by these constants outside doesn't actually change the fact that we're still measuring a length cubed. Right, and so on the left-hand side we have this length squared, and on the right-hand side we have 3 options. And we can already tell by our discussion above that it makes absolutely no sense to say that something with dimensions of length squared equals something with dimensions of length, or equals something with dimensions of length cubed. And so right off the bat, what happens is that these 2 equations, a equals 2 pi r and a equals 4/3 pi r cubed, become absolutely nonsensical and are wiped off the board. And we're left with the correct answer, a equals pi r squared, from these 3 options that were given. So whether these options are from memory or they're multiple choice options on an exam, dimensional analysis is a really powerful technique you can use to tell you if something you have in front of you kind of makes sense or totally doesn't. Right? It doesn't guarantee that area is exactly pi r squared, but it at least doesn't rule it out, whereas it rules out the other options. Okay, let's talk about example 2 here, and what you see is I've drawn a parabola, and we're not going to talk about the mathematics of parabolas too much, as interesting as that might be. Instead, we're just going to talk about the physical implications of having quadratic equations in your analysis, right? So let's say we have a general parabolic equation, which is ax squared plus bx plus c equals 0 in standard form. And let's say that in physics we got this equation to solve for the position x of some particle or some object. Now at first you might think, well, just like a equals 2 pi r, this equation also doesn't make sense, because if x is a position, it has dimension of length or distance basically from the origin, then x squared has dimensions of length squared, and x has dimensions of length, and we're trying to add these 2 things together, and surely that doesn't make sense. But what you're forgetting is that some of these coefficients are arbitrary variables, right? So a, b, and c aren't just numbers, they can actually mean things. And usually, if you're correct in your physical analysis and you get an equation like this, then those constants themselves will actually be quantities that have dimensions. So for example, let's say that a has dimensions of length, whatever it may be, and b has dimensions of length squared, and c has dimensions of length cubed, right? If this is just what happens to be the case when you do your physics and you end up with this equation, then this equation actually makes sense, because then if you multiply a length by x squared, you get length cubed. And if you multiply a length squared by x, you get a length cubed, and c is a length cubed, and it does make sense to add all of them together and solve that equation for x. So that's something that you have to be aware of when you're doing physics, is that some of your coefficients, unless they're pure numbers like, like we had before, like 2 pi or 4/3 pi, unless they're pure numbers, they can also have their own dimensions that play into these equations and that you have to account for when you do dimensional analysis. Right, now on the topic of dimensionless numbers like 2 pi and 4/3 pi, let's talk about what happens with dimensionless quantities, right? Because you can get these not just by having pure mathematical numbers, but also by taking ratios of physical quantities to ratios or to quantities of the same dimension rather. So let me give you another example. Let's say I am a human and my height is precisely 6 feet tall, which actually happens to be true. And let's say I have another human friend, that may be less true, and this human friend is precisely 3 feet tall. Let's say my imaginary human friend is approximately 3 feet tall, right? So if I want to ask the question, how many times larger am I than my friend in height, I'd simply have to take the ratio, 6 feet divided by 3 feet equals 2, right? And what you'll notice is that I'm dividing something that has dimensions of length by something that has dimensions of length. And the result, of course, has no dimensions at all, because length and length cancel out in the numerator and the denominator. And so this 2, this ratio that we got between one length and another, is as pure of a number as the 2 that comes along in 2 pi r. Okay, so this is just a pure dimensionless quantity, even though it came from physical quantities that had dimensions of length, because it's a ratio of them. Similarly, if you're counting things, right, like let's say you're just counting the number of ducks in a pond. Let's say you have counted 6 ducks in a pond. Right? What you'll find is that 6 ducks in a pond is also just a pure number. It doesn't have any sort of dimension at all. It's obviously not a length or a time or anything like that. It's nothing at all. It's just a number in the same way that 2 is just a number, in the same way that pi is just a number. It's just a mathematical quantity that has no physical dimension. Another useful, or I should say common application of taking ratios to get dimensionless quantities is actually when we talk about angles. So let me draw a quick circle here. And let's give this circle some radius r. And let's say we're trying to measure some angle theta from the x-axis, like this. Right, now if you've ever worked in radians, what you should know is that this angle theta is just a ratio between the arc length that it subtends, let's call that s, right? So s is the length from this point to this point. So it's a ratio of s to the radius of the circle r, right? That's just the angle that it is. It's the ratio of the arc length to the radius. And so of course, because this has units of length, and the radius has units of length, you'll find that the angle itself has no dimension at all. And the fact that this angle theta is dimensionless is actually what lets you do things like take functions of theta, like sine of theta, or any trigonometric functions for that matter, because it wouldn't make sense to take the sine of, let's say, length, right? You can't really take sine of 2 meters. That's ill-defined. It doesn't make sense in the same way that adding 2 meters to just 5, dimensionless 5, wouldn't make sense. Similarly, if you do like 2 to the power of x, x has to be dimensionless there as well. Or if you do the log of x has to be dimensionless there as well. Or else these things really just don't make sense. You can't take the log or an exponential of some quantity that has dimensions. It just doesn't make sense. The output of these things is also dimensionless then, right? So if you start out with something that doesn't have dimensions at all, then sine of that angle won't have dimensions at all, or 2 to the power of that thing won't have dimensions at all, and so forth. Now, there's something that's been lurking in these discussions all along that we haven't really touched on yet, and that's the fact that quantities that have the same dimension can still be measured in different ways, right? For example, the dimension of length, we've already talked about measuring it in inches, and just now we've talked about measuring it again in feet, which is a completely different way of measuring it, right? And similarly, we talked about angles being a ratio if you think about them in terms of radians, but what if you measure an angle in degrees? What's the difference there? And so this takes us to a completely separate discussion on units, which again are just different ways to measure things that have the same dimension. And let's start off with a really typical example, which is temperature, right? We all know that temperature can be measured in different units because here in the United States, we measure it in degrees Fahrenheit. Practically everywhere else, they measure it in degrees Celsius. Or if you're talking to a scientist, they're going to measure it in Kelvin for the most part. So let's talk a little bit about how that works and what the relationship is between all of these units. And because I'm here in the United States, I'm going to go ahead and start working in the Fahrenheit system. So let's say I have a thermometer over here on the left side, and it's a very special thermometer, mind you. It's infinitely long, so it goes infinitely far up and infinitely far down. But right now the thermometer is over at this mark, which I'll call 32 degrees Fahrenheit, because it's precisely freezing outside. Okay? And let's say I mark up my thermometer, so I have a way to measure how many degrees Fahrenheit there are, such that each mark corresponds to 1 degree Fahrenheit. So this is 33 degrees Fahrenheit and so forth, and the mark below it would be 31 degrees Fahrenheit. You get the idea. Right, so this is just a variable that we're using, that we're measuring, that lets us know what temperature it is, depending on how high up the thermometer is filled. And there are two things that we had to do to set up this variable, this degrees Fahrenheit united variable, which is we had to pick a starting point, which was 32 degrees in this case, and we had to pick a unit length, basically, which is how spaced on the thermometer are each degree, or is each degree going to be. Right? So in this case, we did that kind of arbitrarily, but regardless of how we did that, we'd get a valid way of measuring temperature, because regardless of where the thermometer is pointing, we'd have one specific number to tell us what temperature it is. But these different ways of marking up the thermometer are precisely what different units are. So let's say I have a friend, his name is Bob, and Bob measures temperature narcissistically in degrees Bob. And degrees Bob are defined like this. Instead of saying that 32 degrees Bob is where freezing is, freezing temperature is defined to be 0 degrees Bob. So I'll put degree B to mean Bob. But Bob is my friend, and so Bob agrees with my definition of how each unit on this thermometer should be spaced out. So he uses the same markings that I do, but now he calls them, instead of 32 and 33 degrees Fahrenheit, he calls them 0 degrees Bob and 1 degree Bob, and so forth. And of course down here is minus 1 degree Bob all the way down. Right, so all of these temperatures go from minus infinity to infinity on this thermometer. Okay, so Bob has his own way of measuring temperature, and that's perfectly fine. He still has a number for every possible temperature it can be. Some of you might see where I'm going with this, right? The next thing that we can do is we can define the Celsius or the centigrade scale. And the way that the Celsius scale is related to Bob's scale is that the Celsius scale also chooses, as Bob did, to make 0 degrees where water freezes, but it wants there to be exactly 100 units between where water freezes and where water boils, which means that even though 0 degrees Celsius is going to line up with Bob's 0 degrees, 1 degree Celsius is going to have to be a larger tick mark away from the 0 point, so maybe somewhere up here. And similarly, minus 1 degree Celsius will be further away from 0 down here. And how do we know that these tick marks need to be larger? Well, that's simply because we know that in Bob's scale, the number of tick marks between freezing and boiling points of water is going to be the same number of tick marks as on the Fahrenheit scale. In other words, it's going to be the same as 212 degrees Fahrenheit minus 32 degrees Fahrenheit, which is simply 180 degrees, or 180 tick marks. Now, if we only want 100 tick marks between 0 and boiling on the Celsius scale, then that means that each tick mark is going to have to be that much bigger, right? So in 100 tick marks, you have to cover the same distance in temperature that the Fahrenheit system or the Bob system covered in 180 tick marks. And of course, these go all the way up to infinity and all the way down to minus infinity at the same bigger step size. So this is a second way of changing the units we use to measure the same quantity of temperature, not by changing where the 0 point is, but instead by changing how big a single degree is. The final thing we can talk about is the Kelvin scale, which is used a lot in science because the 0 on the Kelvin scale has a special meaning. It's called absolute 0, and it's where, at least in gases, all motion stops. And because we're changing the 0 again when we go from the centigrade scale to the Kelvin scale, what 0 degrees Celsius means is actually going to end up being somewhere around 273.15 degrees Kelvin. Now the spacing in the Kelvin scale is actually adopted from the Celsius scale, which means that when you have 1 degree Celsius, that's going to be the same spacing away on the Kelvin scale. In other words, that's going to be 274.15 Kelvin. Minus 1 degree Celsius will be 272.15 Kelvin, and so on, again to plus infinity and to minus infinity. Now, what exactly we mean by negative infinite temperatures when we're talking about Kelvin, where absolute zero is when all motion stops, that gets a little bit tricky. But the truth is that in physics, negative temperatures do exist, even on the Kelvin scale. They just occur in very exotic systems, so we try not to talk about that too much. Now, you might be understandably frustrated with this, right? Why do we need, you might ask, all of these different ways of measuring temperature, or measuring any dimension for that matter? Why can't we all just agree on one best way to measure everything? One best unit to use for length, one best unit to use for temperature, and so on. Otherwise, it's just going to be a mess, right? It's going to be confusing. And the answer is that we can sort of do that, but not entirely. So let's go into that a little bit, right? When I say we can sort of do that, I mean there's something called SI units, right? This stands for the International System of Units, and they're kind of a standard or default set of units that we use when we're measuring different quantities or different dimensions. So let's talk about a little bit what these what these units are. So when we're measuring length in the SI system of units, the convention is to use meters. When we're measuring time, the standard is to use seconds. When we're measuring mass, the standard is to use kilograms. And we also mentioned electric current, which is measured in amperes, and we mentioned temperature, which is measured in Kelvin, but these are the three most important ones, or the most commonly used ones, perhaps I should say. And so this system is often called the MKS system, which maybe I wrote it in the wrong order, but stands for meters, kilograms, and seconds. And one thing that you can ask is, well, okay, so it's great that we can use meters, seconds, and kilograms consistently everywhere and every when. What exactly is a meter? Right? How do I know that when I say meter, I mean the same thing, the same physical length as when you say a meter? What if my meter stick is just a different length than your meter stick, but we're both calling it 1 meter? Right? So when we're talking about conventions like this, like the SI system of units, we need to be very precise about what exactly a meter is, so that everyone around the world, no matter what their meter stick looks like, can agree on what a meter is. And to be precise, it requires doing some strange things, okay? So these definitions of what a meter is and what a second is and so on aren't going to be the most intuitive thing. But let's talk about that a little bit, okay? So you understand it's going to be strange, but it has to be strange to be precise. So let's see, what's a meter? 1 meter is defined as, so I'll write a triple equal sign, that means defined as. 1 meter is defined as the length traveled by light in a vacuum. I'm not going to write that because I don't have space, but in a vacuum, in precisely this time, in 1 divided by 299,792,458 seconds. Okay, so light travels super duper fast in a vacuum, and in precisely this fraction of a second, it travels what we define to be 1 meter. What's a second? We haven't even gotten to that yet. Well, that's also going to be important, and that's also going to be weird, but again, it's weird to be precise. So precisely what we mean by a second is the time it takes for a particular isotope of cesium, right? This is cesium-133. It's an element that occurs in nature. So it's the time that it takes for this particular isotope to undergo a specific decay 9,192,631,770 times. So time taken for cesium-133 to undergo this many decays on average. So obviously you can tell that cesium-133 decays very, very frequently, right? In a second, it decays 9 billion times. But we picked this specific number to define exactly what we mean by a second. And it gets weirder for kilograms and so forth, and we don't have to go into all of that here, but I'm sure you can look it up on Wikipedia or something like that to see what all of these different SI units are defined as. Okay, so we have this SI system of units. But the truth is, it's not ideal to just measure everything in the same exact units, right? I mean, you can measure your height in meters if you wanted to, but if you wanted to measure the distance to the moon, there are more convenient unit systems to define, right? There are more convenient scales to use. At least maybe you'd want to measure it in kilometers or something like that, right? There are just too many meters to be comfortable talking about those big distances, in meters. Or similarly, if you're talking about the size of a bacteria, there are different scales, different units that you want to use to talk about really small distances, because it's going to be some very small fraction of a meter that you don't want to write out every time when you're talking about these small distances. So despite having this SI system of units, we also need to put something in place to where we can talk about different scales of units. And to that end, in physics, or in science in general, we use these metric prefixes, right? And we've already talked about, for example, the difference between a meter and a kilometer, right? A kilometer is precisely 1,000 meters. And, if we want to talk about inches and feet, we have, of course, 12 inches equaling 1 foot, and so on. But these prefixes actually tell you in orders of 10 what the relationship is between some sort of base unit and the actual unit that you're using, right? So obviously, there's no prefix between inches and feet because that's part of the imperial system. But when you're going from meters to kilometers, that's in the metric system, and so this kilo prefix in kilometers just means 1,000 meters. And I've underlined here some of the most common ones that you might have seen. So, centi down here at 10 to the minus 2 means 1/100th of whatever unit you're using as your base. So a centimeter is 1/100th of a meter, right? Or a millisecond is 10 to the minus 3 seconds, or 1,000th of a second. Nanotechnology is something that we've probably all heard of by now. And if that were true to its claim, if it were to be taken literally, nanotechnology would have to be 10 to the 9, or 1/1000th, the size of ordinary technology. On the other end, we have mega, giga, and tera, which are much bigger than their base units, right? So giga means 10 to the 9, or 1,000,000,000 times bigger than the base unit. So if you measure, for example, data in gigabytes, each gigabyte is 1,000,000,000 times bigger than the base unit, which is a byte. Okay, so these are the ways that we use these metric prefixes, but I don't want to give you the wrong idea where these metric prefixes and units in general are specific to things that have dimension, right? I mean, certainly we've talked about length here, meters and kilometers, and we've talked about time, seconds and milliseconds. But there are also quantities that don't have any dimension at all, like angles, that can be measured in different units. So let's talk about that for a second. Let's talk about the units of dimensionless quantities. And let's go back to our favorite example here, where we're counting the number of ducks in a pond. Okay, so number ducks in a pond. I'll just abbreviate it as number ducks for now. But instead of just measuring, say, some number of ducks in a pond, we can measure that same quantity, which remember doesn't have any dimensions, in a different unit. For example, the number of dozens of ducks in a pond, or number dozen ducks for short. Right, and these two things are obviously related. The number of ducks is just 1/12th of the number of dozen ducks. Right, because 1 dozen ducks is exactly 12 ducks. You should probably know that by now. So these are just different ways in which we can measure the same thing, even though that thing is unitless. And if we wanted to go a step further, if we wanted to use some of the metric prefixes to choose even different units, we can talk about the number of kilo ducks, right? And of course, the number of kilo ducks is just going to be, 1 in 1,000 the number of ducks. And why is that? Well, that's just because 1 kilo duck, by definition of the metric prefix, is 1,000 ducks. Now, I'll admit, if you go around ponds talking to strangers and measuring the number of ducks in ponds in kiloduck units, you might get a couple of weird looks. But as long as you're talking to a scientist, they will know exactly what you're talking about when you're measuring ducks in kiloduck units. Okay, let's do maybe a more physical example. Let's go back to this idea of measuring angles in radians versus degrees, right? So we've already said that we have two different ways of measuring angles, right? We've said that radians were the number of, were the ratio of the arc length in that angle to the radius of a circle. And what that means is that a full circle, so what we know to be 360 degrees, is equal to the full arc length, which is just the circumference of the circle, or 2 pi r, divided by the radius of that circle, or r. And that's just 2 pi. Right? So what that means is that in a full circle, we know they're 360 degrees, and we know there are 2 pi radians by definition of what a radian is. So we have this relationship between degrees and radians that we can use to go between one unit and the other. In fact, if we wanted to talk about smaller angles than a degree, because a degree is already considerably smaller than a radian, right? You need 360 degrees to match just about 6 radians. So degrees must be smaller. But if you want to measure something that's even smaller than a degree, you can use even smaller units. So you can use arc minutes, for example. And an arc minute is just 1/60th of a degree. Or in other words, 60 arc minutes go into a degree. If you want to measure something even smaller than an arc minute, you can use an arc second, which, as you might have guessed, is 1/60th of an arc minute, in the same way that a second is a 60th of a minute. And a minute, of course, is a 60th of an hour, in the same way that an arc minute is a 60th of a degree. So these are all different units you can use to measure angles, which themselves are dimensionless, right? So the whole point of this was that even dimensionless quantities can have different units that are convenient for different occasions. So let's be a little bit more systematic about how we can convert between different units in a particular dimension. So initially, maybe let's stick to dimensionless quantities, right? Let's say we have 60 ducks in a pond. And I know that this is going to be a very simple example, but I'm just using it to demonstrate. So let's say we have 60 ducks in a pond, and let's say we want to know how many ducks there are in a pond, but we want to know that number in dozen ducks units. Whoops, dozen ducks. Okay, so how do we find this equality? 60 ducks is how many dozen ducks, right? Well, we know by definition that one duck is 1/12th of a dozen ducks. We said that before. Right, so if we have 60 ducks, we could scale this up a little bit. We can multiply both sides by 60, and we get 60 ducks equals 60 divided by 12, which is 5 dozen ducks. Right, that's the same equation that we had from the definition, but now it's just scaled up a little bit to match what we need. So now we know that 60 ducks is the same as 5 dozen ducks, which makes sense. That seems pretty reasonable. But sometimes things don't scale so nicely. So maybe, is there a different way of doing it that's a little bit more algorithmic? And there certainly is, right? We could take the same thing we started with, the definition that relates ducks and dozen ducks, and we can substitute straight off the bat into what we have already. So let me be clearer about that. We have 60 ducks, but we know that a duck is a 12th of a dozen ducks. And by mathematical substitution, we can just replace the word ducks with 1/12th of a dozen ducks. That is a completely valid mathematical step to take. I promise you, you can treat these units as variables. So you can substitute duck for 1/12th dozen ducks wherever you see it, and you will get a mathematically correct factual statement. Okay? So 60 ducks is 60 times 1/12 dozen ducks, which is the same exact number, 5 dozen ducks. Right? So this second way of converting between units is to just find what the unit you're starting with is equal to in terms of the other units and substitute that in. But there's an even more popular approach than doing that, which is called the multiplying by 1 method. Right? And the way that this works is just to write out this equation that we use to define 1 duck equals 1/12 dozen ducks, right? Write this out as 12 ducks divided by 1 dozen ducks equals 1, right? That's the same exact equation. The only thing we did is we multiplied both sides by 12, so we got 12 ducks on the left. And then we divided both sides by a dozen ducks. So we got 12 ducks divided by a dozen ducks is just equal to 1. And how does that help? Well, it helps because 1 is something that you can multiply anything by and get something that's equivalent to, right? So if we're starting with 60 ducks, we can multiply 60 ducks by 1 to get something equivalent to it. And we know that 1 is the same as 12 ducks over 1 dozen ducks. And what do we end up with here if we do this product? Well, it's actually not something that we were looking for, right? We get 720 times ducks, or ducks squared, divided by a dozen ducks. So this is still a unit that measures how many ducks there are in a pond. Ducks squared per dozen ducks is in fact a valid unit, I promise you, but it's not the unit we wanted. We wanted the dozen ducks unit. And what we have to do to get the dozen ducks unit is actually multiply by a different version of 1, which we get by flipping this fraction, right? If we take 1 dozen ducks and divide that by 12 ducks, we still get 1, because you can think of this 1 as 1 divided by 1, and if you flip both fractions, you still get an equality, right? So 1 is still equal to a dozen ducks divided by 12 ducks. And so if we start with 60 ducks, and we multiply by 1, but now this new version of 1, which is 1 dozen ducks, divided by 12 ducks, then we get out exactly 5, and of course we get this ducks variable canceling with this ducks variable in the denominator, and so we're left with 5 dozen ducks. And this is in fact the unit we wanted, and we got the same answer as we got before. 60 ducks equals 5 dozen ducks. Okay, so make sure you don't follow the pitfall of using the wrong fraction when you're multiplying by 1, or if you do, at least check to see if the unit you're starting with cancels out with something in the denominator, because that's what you want to happen, right? You want the unit you're starting with to go away, and the unit you desire to come in. So that's why we want dozen ducks in the numerator of this fraction, and ducks in the denominator. Okay, so these are the 3 ways to convert between units in this very simple example. Let's go on to maybe something a little bit more mathematically oriented. So let's talk about degrees and radians again, for example. Let me erase some of this. And let's say that we have a measurement of an angle, right? Let's say we measure an angle to be 90 degrees. And let's say we want an equality to some number of radians. Right? How do we convert this measurement of an angle from degrees to radians? Well, we already have by definition, or at least by what we found above, that 360 degrees, 360 degrees, is precisely equivalent to 2 pi radians. Right? This is a fact, this is an equality that we know to be true from the definitions that we used before. So if we want to use the multiplying by 1 method, and we're going from degrees to radians, we want to come up with a fraction that has degrees in the denominator and radians in the numerator that's equal to 1. And it's easy to do from here, right? If we divide both sides by 360 degrees, then we get 1 equals 2 pi radians over 360 degrees. And so we can take our original quantity of 90 degrees, multiply by 1, which is now this fraction of 2 pi radians divided by 360 degrees. Notice that degrees are units, right? So degrees cancel out here in the original quantity and here in the denominator. And what we're left with is 90 times 2 pi divided by 360 in units of radians, right? So 90 divided by 360 is just a quarter. So we have a quarter times 2 pi, or pi over 2. Pi over 2 radians is the same exact thing as 90 degrees, because we started with 90 degrees and we just multiplied by 1. Okay, so to give you a final example, let's talk about some distances. Let's say we have a running track that's exactly 3 kilometers long. And let's say that we want to know the measurement in centimeters. Right, so 3 kilometers is how many centimeters is the question that we're trying to answer. Why do we want to know how many centimeters are in 3 kilometers? Maybe we're trying to fill the running track with pennies, and each penny is a centimeter in diameter. So we want to know how many pennies will fit on the running track, right? This is a very contrived example, but I promise you it's quite realistic in the real world, you know? You often put pennies on running tracks. Okay, I'm not talking about the right thing here. Let's talk about unit conversions. 3 kilometers to how many centimeters? Well, this is a little bit tricky because right off the bat, it's easy to go from kilometers to meters. It's a little bit harder to go from kilometers to centimeters, right? But we can do this in 2 steps. We know, for example, that 1 kilometer is the same as 1,000 meters because that's what the metric prefix kilo tells us. We also know that 1 centimeter is the same as 1/100th of a meter because that's what the centi prefix tells us. So we want to form a fraction that's equal to 1, has kilometers in the denominator to get rid of that original unit, and centimeters in the numerator. So let's see how we can do that, right? We can start by writing this as 1 equals 1,000 meters divided by 1 kilometer. And then we can write this as 1 equals 1 centimeter divided by 1/100th of a meter. And of course, 1 times 1 is still equal to 1. So if we take 3 kilometers, which is the quantity we're working with, and we multiply by the first fraction, whoops, not equals, but we're multiplying, so times 1,000 meters divided by 1 kilometer, and we multiply by the second 1, which is 1 centimeter over 1/100th of a meter, then what we end up with is, in terms of units at least, this kilometer unit cancels with this denominator, this meter unit cancels with the next denominator, and what we're left with is just centimeters in terms of units. And in terms of numbers, we have 3 times 1,000 times 1 over 100. And fractions tell us that if you have 1 over 100 in the denominator, that's the same as 100 in the numerator. So really we have 3 times 1,000 times 100, or I can write that as 3 times 10 to the 5th, and again the units we're left with is just centimeters. So I happened to get this on my first try, but you can play around with some of these conversions until you find a factor of 1 that has the right units ending up in the numerator after everything cancels out, right? Or of course you can do the substitutions that we talked about before. You can, for example, substitute this meter equals 100 centimeters into here, into that equation, and what you'll end up with is 1 kilometer equals 1,000 times 100 centimeters. And then you can substitute that kilometer into here, and you'd end up with the same answer, 3 times 1,000 times 100 centimeters. Okay, so there are different ways to do this. Some are easier for some people than others. But hopefully this has given you an idea of how to go about doing unit conversions, maybe how units work in general, and also what these different dimensions are that we use in physics, and how dimensionless numbers can also play a huge role in what we do. If you have any questions about anything we've talked about, or really anything at all, feel free to leave them down in the comments below. And other than that, I hope to see you back here for the next episode of Central Physics Reviews.